we're a little bit early.
Microphone.
Do I need the microphone? Can you hear me, everybody?
Also for the record. For the recording.
Oh, I need the microphone for the recording. Yeah. Okay. Can you hear me like this?
No.
Like this?
Yeah.
Better?
Yes.
Is this better?
Yes.
Okay. We are a little bit early, so before we start the actual presentation, for those of you who do not know me, I will take a couple of minutes to introduce myself. My name is Boris Shingarov. I started my career as a theoretical physicist, and then by pure accident I discovered the beauties of Smalltalk, and that got me immediately hooked up. So for the next degree I said, okay, well, the next stage in the university will be research in Smalltalk execution engines, and well, after that I spent time writing the VisualAge Handbook that was published by IBM. I spent a few years with the Object People, doing various projects, including Toplink and various customer projects. I spent a number of years at OTI. I did a bunch of consultancy for Smalltalk and Java customers on my own. And right now I am working on the virtual machine for VisualWorks, which is a Cincom product. But this thing that I will be describing today is a result of some tryings and experimentation that I've been pursuing for the last, well, more than a decade with Smalltalk VMs and Java VMs, different companies for different customers, and this sort of just summarizes what I think is going to be our general directions for building VMs for the next century. Our computing needs, our landscape of what we do with Smalltalk has changed and is changing compared to the classical Smalltalk machinery of the 90s. I usually like to divide that between what we run on top of Smalltalk, what application workloads are on top of Smalltalk, versus what the virtual machine is running on, that is the actual hardware. And the change in the last years has been profound. The workload on the Smalltalk runtime, a typical application has changed. It's not just your sequential workstation type workload, but we have moved up into very complex concurrent workloads in the data center, especially when we're talking about big data customers. And we've moved down where we have severe constraints when you are running Smalltalk in an embedded space on an embedded processor, and sometimes on an embedded microcontroller, which may not even have an MMU. And when you are receiving a bug report from a customer today, because of all the complexities of what's happening in the VM, because of the inherent parallelism of the workloads, your bug may be now happening because of the complexity of race conditions in the parallelism. It may be because of complexity of compiler optimizations that are there. So if you just take a normal, traditional way of debugging a VM bug, you might be staring at it for weeks and months and not making any progress. So you need to think about reorganizing the way how you work on the VM to account for that complexity and to enable you to adequately look at what's going on in the VM in the presence of that sort of complexity of today. Normal high-level debuggers do not generally work. This is not what they are. This is not what they are meant for. These are not. Smalltalk VM is not a C application. You normally violate all kinds of assumptions that the debugger is making. If you're trying to understand what the native code is doing, what the native translated code is doing, then a debugger like GCC will be not adequate and just not useful. But even if you are inside the C runtime, your native code, your glue or the native code itself might have done something to the state of the memory or to the state of the registers of the processor that completely screw the GDB's idea of what things are, and your debugger is just lying to you. So you cannot debug using normal traditional tools. Solutions that are based on in-band debugging, and I will get to the idea of in-band in a moment. But something like Sun Ditrace does partially help, because you can take the many complex things and instrument the VM with Ditrace scripts, and it does take off some of the complexity, but it only helps partially, because there are still the VM does a lot of things that break traditional tools' idea of what an application running in user space does. It just those assumptions are not necessarily true inside a Smalltalk VM. Optimizing performance of a Smalltalk engine. The idea of what is meant by performance is has radically changed as well. The traditional idea of let's make Smalltalk go as fast as possible. The idea of the 90s, well, we basically reached what we can do there. We already have very fast peak caches. We have JIT using the instruction level, parallelism, hardware features. Well, that traditional model no longer holds, either because of the workloads, which is what we run on Smalltalk, or because of the processors that we're running Smalltalk on. For example, there have been some big data customers whose applications challenge the model of object memory as a graph of objects. What they are complaining about is that, well, hey, your Smalltalk is spending 90% of time just marshalling and unmarshalling objects on FFI when calling operating system functions. So what we need is we need to change that to some sort of packed object representation, so we don't have that much FFI marshalling overhead. But also what that gives us is it would improve cache performance, so we're not chasing pointers all the time. But that complexity cannot be dealt with when we are using traditional debugging tools, in-band debugging tools. And the new generation of hardware that we're running on, the multi-core chips, that's dictating radically new performance metrics, such as if you're running on an ultra-low power microprocessor, an ARM running on a battery power device, your performance metric is no longer let us send as many byte code, as many message sends, or interpret as many byte codes per second as we could. The new performance metrics are something like battery usage. You have a certain time to do an operation. It's not really performance critical, but what is critical is how many watts you spend on reacting on a mouse click to redraw your screen. And when we say optimize the generated code, right now I'm not aware of any Smalltalk VM which is trying to optimize for that sort of metrics as opposed to the traditional, well, let's just run faster. So that's what that sort of metrics is what I mean when I say what we run Smalltalk on. So let's see what is this new hardware, what is this radical change in the hardware that we're running Smalltalk on. Dave Patterson, the president of ACM, gave a presentation where he talks about wall that the Moore's law has hit. And it's design cost wall, it's software legacy wall, it's power wall, it's memory wall, and it's ILP hardware features wall. And so we're talking about end of the classical era of constant improving of the performance of uniprocessors. So we are out of we're at the end of uniprocessor era. We need to look at what multi-core has to bring in, what ultra-low level power consumption chips bring us, and what that means to Smalltalk software. So the changes are in several things. The design cost wall is that when somebody comes up with a new chip or an idea for a new chip, traditionally, if you are a researcher at Caltech, let's say, you go to the lab, you build your idea into a functioning chip. You show, oh, okay, well, this chip is running 3 times faster than the previous chip. So, okay, well, here's how we optimize things. Today, no researchers can build believable prototypes simply because, well, to build an actual processor, you're talking about producing masks at a cost of, $100,000, $200,000, and no one can afford that. The usual way of looking at software versus hardware flexibility was that, well, the machine, the actual hardware, was hard to change, and you can be pretty flexible with software. You just, okay, well, let's just write new software because that's just writing new lines of code, right? Well, not quite now, because the body of legacy software is so big that you cannot really change software. But hardware, you can be more flexible with hardware. So that's the software legacy wall on our previous slide. It used to be that you were limited by the number of transistors that you can put on a single chip. And power, well, okay, well, it's just gets more hot. Well, we're gonna put a bigger fan on it, or bigger thermal sink on it, and that's okay. So let's just clock it faster, and it's gonna go faster, and the transistors were a limiting factor. Well, right now, the transistors are essentially free in the sense that you can easily fit more transistors on a chip than you can afford to turn on in sense of power. You can put as many transistors as you want to, but when trying to turn the thing on, well, what's going to happen is that your chip is going to melt away because of the power consumption. So this is the power wall on the previous slide. The performance of the memory hierarchy is very different now. Well, it used to be that multiply is happening in many cycles, and essentially on an old microprocessor, well, all of your instructions are the same. You have, like, in the handbook for 8086 processor, you say, well, this instruction is 1 cycle, this instruction is 1 cycle, this instruction is 2 cycles, this is 1 cycle, and then, well, multiply is, let's say, like 32 cycles. And well, now what you have is that you have addition or multiplication in a cycle, or in half a cycle if you're like dual issue processor, but then a cache miss, an actual memory access, costs you 200 clock cycles. So your patterns for optimization and what you have to watch for is completely different now. And what's worse is that there is not this is not a simple lookup in the book anymore. Like you used to be able to say, oh, okay, well, this instruction is taking 3 cycles. That's what's written in the processor manual. You cannot just tell that, because, well, it could be one cycle, or it could be 200 cycles, depending on whether you need to access memory or not. So you've got the memory wall, and well, we've pretty much come to the end of what you can do, or what you can achieve with building more instruction level parallelism hardware. In the last 20 years, we were building bigger and better RISC processors, advances in compiler optimizations, in hardware with out-of-order execution hardware, with very large instruction width, with speculative execution. All of these advances used to give us a new boost in instruction level performance every year after year after year. Well, that has come to an end. We can build bigger and better ILP hardware, and there's very little gain when we try making our processor any faster. So we're basically stuck at where we are for a number of years now, and this situation is not improving. We're at the same level of performance. So how do we solve these problems of not being able to understand the complexity of what's going on in the VM, of not being able to observe what is happening in the processor when the VM is running? Well, the traditional way is in-band, and by the band I mean the communication, quote unquote, of the processor with the VM. So well, the word communicates should be taken as a rough analogy, because, well, they're not really partners in this communication. The VM is executing on the actual processor. But you can think about the instruction stream as VM talking to the processor, and things that are coming back from the processor to the VM, well, sort of coming back from the processor to the VM, like flags, the results of which branch is taken or not taken, the interrupts that result from internal or external to the execution of the VM. You can think of them as a bidirectional sort of communication channel between the VM and the processor. And when you use an in-band observation agent, such as a classical debugger, they are inherently limited in scope of what you can access and scope of what you can look at, what you can change, which aspects of the execution of the VM are observable through such a debugger. And they are inherently destructive to machine state. Like, for example, if you put a classical breakpoint in the VM, and then you hit that breakpoint, and now you're executing the debugger. Well, guess what? You have executed now, several thousand instructions of the debugger itself, and that GDB code has preempted whatever was in the caches of your VM, so that information is gone. So if you're trying to understand why your VM is thrashing on data cache access and going to the memory all the time instead of using what's in the cache and stalling all the time and therefore is 200 times more slow than it is supposed to be if it were not thrashing on the dcache, well, all that information is gone as soon as you hit that breakpoint and start executing the instructions of the debugger. Well, not that it would help anyway, because, well, the cache is invisible to your debugger anyway, so it doesn't help at all. So what I have proposed, and I'll show you some of this, how to do this. What I've proposed is that we do out-of-band observation of what's happening between the VM and the processor. So it's out-of-band in the sense that the channel of communication is completely outside of the processor architecture. That is the software visible model of the processor. So it's invisible to both the VM and the processor. Neither of them are affected by the instrumentation through which you're observing the communication between the VM and the processor, nor the processor is aware that there's debugging going on. And it could be done at varying levels of fidelity, of detail. So, for examples, you can do functional simulation of the processor. Well, the simplest way of doing this is running on just an instruction level simulator such as QEMU, for example. Well, I don't know how many people in this audience have used the processor simulators. Like, how many people have used QEMU? Okay. 2 people. Well, how many of these 2 people have used something that has more fidelity in simulating the processor, such as Cynix or GEMS or anything beyond QEMU? Okay, well, I see no hands. Well, I have good news for you. There are simulators that model the processor and the whole machine at a level which is much more detailed than simply emulating the execution of the instructions. There is a whole class of software that will, to a very great level of detail, model things like the microarchitecture of the processor. It will model the different stages in the pipeline of execution of your instructions. So you can actually model things like, well, this instruction is gonna take, well, one cycle when it gets fetched, and then the next cycle it's gonna be decoded, and then it's going to be executed, and then it's going to be retired. And you can model things like out-of-order execution. You can model things like your cache hierarchy. You can model things. You can model things such as, well, okay, well, my cache is warming up, and now it's full, and which instructions exactly are gonna cause a cache hit or a cache miss. And they will allow you to execute whatever code you write as part of a module that you write for your simulator, to actually see what parts of the VM, or exactly which lines of the code in the VM are causing this particular pipeline stall. The other way, the other example of how you can observe the execution of the VM at the lowest level, how it interacts with the processor, is to actually look at the schematics of the processor, or of the HDL, the hardware description of the actual processor hardware, and you could either implement that on an FPGA and having instrumented that processor with something which is aware that there is a Smalltalk VM executing on me, and I can catch various conditions, and I can report up to the introspection system about certain things that happened in the Smalltalk VM that are executing on this processor. So we could modify this processor and implement it in actual hardware, and it will cooperate in our debugging of the VM. So we don't just have a software debugger, but we have the actual chip on which the VM is executing is aware of Smalltalk and can tell, oh, the guy is performing a message send. Let me report this, or modify some statistics table to that sort of thing. If you want even more detailed statistics or picture of what's happening, you can take one of those simulators that the processor companies, like the semiconductor companies, use for verification of their hardware designs. What they do is they put that schematics of the processor, they emulate everything that it does in software. Well, you can run a whole operating system and a whole application on top of that. So one of the way what we do is we take a Smalltalk VM and use the processor verification software to see what's happening inside the processor at a very, very detailed level. So the full system simulators, the software things, well, there's a bunch of them that I played with for the purpose of evaluating of what's going on inside the VM. One classical one is Cimix. Cimix is a commercial product for Virtutech. Been around for a very long while, I think since 97 or 8, something like that, has matured and now is sort of a classical way of doing these things. There was a project at a University of Washington, I believe, to expand on that Cimix work to better model the Spark hardware and they built a very detailed model of the Spark processor and its caches and the memory hierarchy in a Spark machine. In order to do that, they had to make their own timing model to more precisely model the timings of the execution, so that they could do things that vanilla Cinex doesn't do, because in pure vanilla Cinex, if you don't modify it, at least the older versions that the GEMS guys were using, it's just one instruction equals one cycle, and that's obviously nowhere near anything good enough to understand the performance of, well, I think like a Smalltalk VM. So what they did, they built a new timing model, and they used that to precisely model the timing of execution of the Spark machine. M5, they had their own simulation framework independent of Cinex. M5 is open source, GEMS is open source, and they have combined these things into GEM5. These guys are that's a full open source implementation that can simulate a bunch of different processors and a bunch of different processor architectures to a very, very great level of detail. You can see exactly what goes into performance of cache and why your software is stalling on memory access, and why let's say if you are compiling things, how your compiled code is non-optimal, and then where your range prediction doesn't work, and so on. And well, there's also OVP Sim. I think it's a very interesting simulation software, but I don't really know much about it, and I haven't tried running an actual Smalltalk VM on top of that to see how much OVP Sim can do for Smalltalk. The characteristics of full system simulators is all timing abstractions, and there are different timing abstractions, and there's different levels of accuracy. Well, the easiest is software time, for example, QEMU and IBM TechSim. What they do is they just execute instructions, basically. You don't get any timing information. You just don't get any timing information. There is the TLM, the System C modeling specification defines different levels of timing abstraction, loosely timing, approximately timing. So you have to specify, or you have to decide for yourself, do you want speed versus accuracy? If you are really interested in where your cache is getting in the way, cache performance is getting in the way, you probably want to be more accurate. But you want to wait all the way for the operating system and the VM to come up before you can start looking at that much level of detail. So what you do is you can switch between the different timing abstractions. You can quickly bring up the operating system and then start looking at the details. There is observability benefits. A full recording of the simulation makes possible some arbitrarily complex analysis of the interaction between, let's say, your processor and your memory. There's nothing hidden, like actually on an internal bus of a processor. You can check, you can do snapshots of execution, and because of that's happening, you can walk back and forth. You can dynamically reconfigure things, which is something that actually happens in real life, and you cannot really do that with a normal debugger. What's interesting is that everything is exposed as an open set of APIs, and you have everything, devices, memory, even the time model. And what's most interesting is that that model can be completely aware of software running on the simulated system. So if you're running an operating system, it's not an opaque thing. It's whatever executing on top of me. Well, these are just instructions. You're not limited to that. You can say, well, I know that there is Linux running on top of me. So I can say, oh, okay, well, right now this process is scheduled, and I can notify notify the introspection module that a context switch has happened. So people have written full symbolic debugging modules, and that enables us for the simulator to be fully aware of Smalltalk. So we're going to do a demo. We're going to get a machine and insert a magic instruction breakpoint there. Something, it's something that makes no sense in a real executing code, but we're going to use that for signaling, to signal to the host that something has happened, that we have reached a point in the execution of the VM that is of interest to us, and now it's time to look at what's happening in the VM in greater detail. So there are some already well-defined accepted instructions, and on x86 that's exchange BX with the 66 prefix and the instruction encoding, which limits it to 16-bit in 32-bit mode. So you're not likely to encounter this instruction in actual executing software. On ARM, there are some different things, and then you will see that if we enable that, that's actually only happening where we insert it. So we're gonna use the open source implementation for an example. You can do this with any VM. And the way how this is done in cog, you just take in the compiler, you insert a new instruction that you call the magic instruction. So at the latest VM sources, if you look at them, there is the abstract instruction and then the concrete instruction, and then the compiler concretizes each instruction. So you have to modify these methods and put in at the end of the list of instructions. You say you say that you have a magic, and in the concretize you insert those 3 bytes as the actual implementation of the instruction, and then the initialize in the compiler. You would send it to reinitialize that table. Now the abstract RTL has the magic instruction in it, and in the actual interpreter, you would declare that you have a new instruction. And then we would like to use it somewhere as to put in a breakpoint. Well, let's say when the VM is asked about the class format of non-int, and put it into some scratch register. So that's the method in the object. It's important to understand what we're doing here. we're not really stopping in this method. We're stopping in the generated encode. So what we're doing, we're not putting breakpoint in this, but we are putting a breakpoint into the encode. And if somebody is interested, I will show you like, on this actual machine. For lack of time, we will skip this. But anyway, who is interested? Yes, I will show you. And then we generate the VM source, we compile the VM, we run under the simulation, let's say, well, something like this. And now, if we execute that with the magic break enable option of the simulator, we're going to stop at the instruction, and then at the Cimix prompt, we can say print registers, and here is, let's say this. So we say that the receiver is in here. That's the linear address, and the Linux process module knows how to translate that linear address into the physical address, and then we can look at what's at that address. Yeah, we get the first 4 bytes at that address. This is my object header. So I see that, oh, okay, well, it's type 2. So the OOP to the class, I'm looking at what is that in my what is my receiver. So I am interested in what class it is. So I need to take the class OOP in header word 2 at offset -4. And so that -4, 40 -4 is 3C. So I'm gonna translate that logical thing, address to physical, and then print the 4 bytes. So this is the object header of my class. And now I can look at the field which is pointing to my string with the class name and print that. So that's very slow way of doing these things and doesn't get me very far. So what I do is this is all it takes to do a module that will implement a new command in Cimix. It's written using the Cimix Python API. You can program through the Cimix has 3 APIs: one for C, one for Python, and one for their own domain-specific language. So what we do is, okay, well, if the last bit of my OOP is 1, then it's a small integer, obviously. Else is, let's say, small header type, which I will show you the code for that. And then if the header type is 3, it's a compact class. Otherwise, we read vert value is a function that translates the virtual linear address and physical address, and we take 4 bytes at this because the word 2 is just below the header, and this is the OOP. We are masking it off the last bits, and then the class OOP is going to be that. And the same way we dereference the name, and then we can just print the actual bytes in the instance variable of the class object. And then we register that function as a new command. And then if at the Cimix prompt, I can just issue the command print class of OOP on the EDX. EDX points to the receiver. So I see that the class of my receiver is this. And then that other one was, that's what the name of the class points to. I can also print it, and I see that the class of the name is byte symbol. So here's how I can do Smalltalk aware simulation in software. Well, closer to practical use of this, how does this get me closer to debugging an actual crash of the VM when a customer reports one? Well, I put a simulation breakpoint, like what we just saw, the magic in the SegD handler of the VM. And because the simulation can be recorded, I can just hit the crash and then step back. So if it's a very tricky timing bug, I don't have to juggle around and trying to hit exactly what the bug is, because if I just step towards the bug, well, timing is changed, so my bug is not happening. But I could be hitting the bug at full speed and then stop it. And because I have recorded all the instructions that I was simulating, I can walk back to a point where I think, and then restart step by step, but it's not like nothing real is going to be happening. It's just going to be replaying what I was recording, right? So because I'm replaying, the timing that the debugger has screwed up for me, it doesn't matter, right? Because it is the timing that was there during the actual execution. And then I can solve bugs that are hopelessly complex when I am debugging on an actual processor. Well, we are sort of out of time, so if anyone is interested in digging even deeper with microarchitectural mode of this, I can show you how to use the microarchitectural mode, and then there is, we can dig even more with more detailed models of what's happening inside the processor. Well, we can go even further. Inside the processor at even more detail. We now have available to us hardware to experiment with different processor designs. The different designs that are available in open source, they're no longer toys. You can have practically important processors and whole system on chips that are used in production and are available as open source. Some interesting ones are OpenSpark, which implements Spark v9, the 64-bit version, I say. The T1 is the actual 8 cores by 4 threads, so it's 32-thread UltraSpark. The actual UltraSpark design released by Sun into open source as the Verilog HDL back in 2007 or 8. Leon 3 is a version of Spark which has been used by European Space Agency, and that thing flies on the International Space Station, running some of the computers up there. We have Storm and some other implementations of the ARM architecture and the whole system on chip. So we can program all that either into an FPGA or simulate that. We are probably, somebody suggested that we do a whole little offsite workshop on doing off-band introspection of a VM running on OpenSpark on the Xilinx Vertex 5. I've brought some development boards with me, so we can see how to program that stuff over JTAG and how to modify the processor so it's aware of Smalltalk executing on top of it. Things. These slides are probably best to that little offsite seminar. If anyone is interested at all how these modified processors can be implemented. We've got even more interesting challenges. This is my last slide, I promise. Some interesting challenges when the criteria of optimization changed when we need to optimize for power, there is it affects your instruction selection, instruction scheduling, and so on. And you have to do explicit power management for these devices, like on ARM, for example. You've got to do explicit voltage scaling because you cannot really run at the maximum speed all the time. Because what's happening is that your power consumption is non-linear in your voltage. It's quadratic. And your speed is at best linear in voltage. So what you have is that you don't want to run as fast as you can. Because if you run as fast as you can, what's going to happen is that this is the time and this is your speed. So in order for your user interface, for example, not to lag, let's say you have 50 milliseconds. And then after that, the user is going to notice a lag. And you've got a certain work to do. Well, you can just say, okay, well, I have a very, very fast Smalltalk VM. So you're done in 10 seconds, or 10 milliseconds, right? So you're done. The speed is this much. Or you could have a slower VM, which is running at that speed, and it's going to finish in 50 milliseconds. So you are 5 times slower, but guess what? You have consumed 25 times less electricity. So if you just run as fast as you can and are done in 1/5 of the required time, and then you sleep for the other 40 milliseconds, well, let's say 1 unit of this 5 is, let's say, one picojoule. So, well, guess what? You are wasted. So you're 25 times instead of 5, right? So because you're 5 times slower here and 25 times the minute. So the difference is 5 times. So you're what? You're 80% inefficient. You could be using 5 times less battery and be still within the deadline, and after which the user does see that your interface is lagging. So the problem is the missing integration mechanism to tell the software, hey, you don't need to run at this speed. All you have to do is you have to run at this speed. That's enough. But that is a problem that is going to take a very, very long time to solve, because we don't have any mechanism to tell the VM, hey, slow down.
I am not swallowing blood anymore.
And, well, there is a couple of references that are completely like straightforwardly related to what I was describing. There's a couple of people apparently doing the same sort of, they're going in the same sort of direction. One is Mr. Wright and Mr. Volchko. Volchko is an old-time Smalltalker. Inside the Sun, he introspected a JVM under simulation, and there's a book of collected papers about simulating processors and full systems. I have the book here in ANSI. We can read through it, if you want. That's it. Does anybody have any questions? Yes.
So my concern is about another word, which is diminishing returns. So I can imagine that you can using this very deep analysis to squeeze a bit more or trade less power to the less power consumption through the less.
Are you talking about this diagram?
Yeah.
Okay.
I mean, you can use the advanced simulation software or advanced simulation
Yes.
systems to squeeze a little bit more. But my concern that is it worth it? I mean, what about diminishing return? How much you can squeeze in the terms that the effort worth the output?
Oh, you don't even have to go as far as looking at any sort of VM. Like you don't even have to look at the Java VM or the Dalvik VM. Because even if you look at what's happening in GCC, what they are now talking about is optimizing for power. GCC has flags saying minimize power consumption on hour. So you can imagine that it would be also relevant in an interpreter scenario. Like if it is important in a purely compiled scenario, just like in an as mainstream scenario as GCC.
Yeah, but I mean, how big is the impact of optimizations? I mean, is it orders of magnitude, or is it just
times? It's times. It's probably not an order of magnitude, but it's several times. It really it definitely is not just measurable, but it's a difference between draining a battery in minutes versus in hours or days. Yes, please.
What would be your short-term recommendation to VM developers, to improve VMs?
Well, you could start by experimenting with or running your VM in a simulated environment, or well, there is already people who are developing their VMs in simulated environments, but for example that would be QEMU. If you are already using QEMU for VM development, you are just not even a step, probably half step away from going into more detailed simulation of what the processor is doing.
Okay, we should stop.
Thank you.
Thanks.